In this video, we're going to work the example problems from section 4.5, which was the introduction to the standard deviation. In this section, we didn't learn how to calculate the standard deviation. We just more developed an intuition for what it meant, which is just as important as understanding how to calculate it. So, okay, the Public Health Service found that for boys age 11 in the Haynes 2 study, the average height was 146 centimeters and the standard deviation was 8 centimeters. Fill in the blanks. One boy was 170 centimeters tall. He was above average by how many standard deviations? So remember, as we've talked about, you have this Haynes 2 study. This was from 1976 to 1980. And they asked, I thought those studies were just from age 18 and up, but I guess not. So they asked people of different age groups questions, but they're just focusing on boys age 11. They asked a bunch of different questions, but we're focusing on the height question. They got the height of a large data set of boys age 11. So that's one, you can think about row or column of data points like in Excel. Just a list of numbers, a list of heights. A list of heights, boys age 11. So a list of numbers you could make, just from a list of numbers, you can make a histogram. A full histogram is made from a single list of numbers. I want to stress this because typically when you think about, if we look here, you think about a graph like this. It has a vertical and a horizontal axis. That's two variables in that graph. You know, height versus weight or something like that. So yeah, for most cases with graphs, that's the way it is. But a histogram is different. A histogram is only one variable, one list of numbers. This represents the count. Or if it's a density scale, it's the percent per horizontal unit, but this is not some other variable. This is just representing the count. This histogram is just a list of numbers. Any histogram is a list of numbers based on a list of numbers. All right. So, okay. So this list of numbers, this heights of boys age 11 in the Haynes 2 study, the average, you could take the average of a list of numbers, right, was 146 centimeters, and the standard deviation was 8 centimeters. So if one boy was 170 centimeters tall, he was above average by how many standard deviations? Well, okay, how far above 146 is 170? It's 24. So what is 24 divided by 8? 3. So this was above average by 3 standard deviations. Another boy was 148 centimeters tall. He was above average by how many standard deviations? Okay, well, he's 2 centimeters above the average. The standard deviation is 8 centimeters, so 2 divided by 8 is what? That's 1/4. So this is by a quarter of a standard deviation. A third boy was 1.5 standard deviations below average height. So how tall was he? So the same question, just kind of from a different angle. How many centimeters is 1.5 standard deviations? Well, if a standard deviation is 8 centimeters, what's 1.5 of 8? Well, 1 is 8, and then a half, 4, so 8 plus 4 is 12, 12 centimeters. This third boy was below average height by 12 centimeters. 146 minus 12 is 134. All right, if a boy was within 2 1/4 standard deviations of average height, the shortest he could have been is what, and the tallest is what? So in the previous questions, they were telling us, you know, in the previous question, this boy was below average height. But if they didn't specify below, then if they're just within 1.5 standard deviations, that could be above or below. If someone just says, look, I'm within this many standard deviations of the average, well, if you don't specify above or below, then it could be either way. And so here, they're just saying, look, a boy is within 2 1/4 standard deviations of average height. So if they don't specify above or below, then that's 2 possibilities of that boy's height. So how many centimeters is 2 1/4 standard deviations? All right, 2 1/4 is 9/4. So 9/4 times 8 18. So the shortest he could have been is 146 minus 18. That's 128 centimeters. The tallest is 146 plus 18. 164. This continues exercise 1. So same question as exercise 1. Here are the heights of 4 boys. Got these 4 heights. Match the heights with the descriptions. A description may be used twice. Unusually short, about average, unusually tall. All right, so what we learned in this section was that for just a general list of numbers in general, so for the most part, thinking about in the context of, a controlled experiment, an observational study, you've got some, for the most part, you've got a list of numbers from some data collection. It doesn't have to be from an experiment or data collection, but in statistics, that's for the most part what we're thinking about. What we learned was that, so a rule of thumb that you can use, this isn't a hard rule, this is just a general rule you can use, is that, well, actually, let's look here first. So for a list of numbers, a general rule is that most entries in the list will be somewhere around one standard deviation away from the average. So most of the entries in the list are going to be within one standard deviation from the average, above or below it. And then very few will be more than 2 or 3 standard deviations away. Okay, so with that in mind, when I look at these descriptions, we're going to match each one of these values to one of these 3 descriptions. When they say about average, to me that's saying that, so most of the numbers are going to be within one standard deviation. So that's a good description for about average. If a number is within one standard deviation, if one of these heights is within one standard deviation of the average, I'll categorize that as about average. Now, unusually tall or short, the word unusually, that would fall under the category of when it said in the section that very few numbers will be more than 2 standard deviations away. They're not talking about a number that's between 1 and 2 standard deviations. They're saying more than 2 standard deviations away. So in that case, I would categorize one of those numbers as unusually tall or short. If a number was between 1 and 2 standard deviations, I would categorize that as like more of away from the average. It's not unusual, but it's not about average. It's away from the average. So I would expect every one of these numbers to be either within 1 standard deviation or further than 2 standard deviations away from the average. All right, 150 centimeters. That's within 1 standard deviation. It's 4 centimeters above average. So that's about average. 130, that is 16 centimeters below average. 1 standard deviation is 8 centimeters. So that's 2 standard deviations away. So I would categorize this as unusually short. 165 that's 19 centimeters away. That's greater than 2 standard deviations. That's greater than 16 centimeters. So that's unusually tall. And then 140 is within 1 standard deviation. It's only 6 centimeters below. So that I would say is about average. About what percentage of boys age 11 in the study had heights between 138 and 154 centimeters, between 130 and 162? Okay, well, as far as percentages, it gave us this general rule. If we don't have the specifics, the actual numbers, we can use this as an assumption. 68% of the entries on the list are within 1 standard deviation, and then the other 32% are further away, so greater than 1 standard deviation away. Roughly 95% are within 2 standard deviations of the average. The other 5% are further away. Okay. So about what percentage of the boys in the study, 11-year-old boys, had heights between 138 and 154? So what is 138? That's 8 centimeters below the average, 1 standard deviation, and 154 is 8 centimeters above. So within 1 standard deviation. We don't have any specific numbers, but a general rule is that to get an estimate, we could say, what was it, 68%? Yeah, 68%. All right, what about between 130 and 162? 130 is 16 centimeters below average. 162 is 16 centimeters above. So they're saying how many are between or within 2 standard deviations. They're not asking how many are between 1 and 2. They're saying how many are within 2 standard deviations total. So anybody that's within 1 standard deviation as well as anybody that's between 1 and 2. Well, we just read a good general rule is 95%. That's a good assumption you can use. Like we saw when we went through this section, they made these assumptions and then they actually calculated the real numbers for it was women, heights of women, I think. 72% were within 1 standard deviation, 97% were within 2. So right, that assumption, that general rule is a good assumption you can use. Each of the following lists has an average of 50. For which one is the spread of the numbers around the average biggest or smallest? Okay, so each of these has an average of 50, and it puts them in ascending order, which is nice. It makes it easy for us to analyze it. They all go from 0 to 100. Average is 50 for each one of these. What else? Well, okay, 1, 2, 3, 4, 5, 6, 7. So there's 3 on each side. 50 is the median here, 50 is the median here, and 50 is the median here. So for each of these lists, the median and the average are the same thing. So if you drew a histogram, it would be a symmetrical histogram, okay? So thinking about the spread then, we just need to look at the numbers on both sides of the 50 and see if the numbers are further away from 50, then the spread is larger. If the numbers are closer to 50, then the spread is smaller. Well, all right, all 3 of these have a 0, and all 3 of these have 100. So let's cross that out. All right. Now, okay, this has the largest spread. You have 1, 2, 98, 99. That's as far away from 50 as you can get, other than 0 and 100. So this is the largest. Okay, which one's the smallest? The smallest spread's going to have numbers that are closer to 50. So 20, 40, yeah, this is right. These numbers are right next to 50. 48, 49, 51, 52. So this is the smallest spread. Okay. Each of the following lists has an average of 50. For each one, guess whether the standard deviation is around 1, 2, or 10. Okay, so they don't put these in ascending order, which is, it'd be nice if they were, but it's okay. We know the average is 50 for each of these. Standard deviation is a measure of the spread of the numbers around the average. So we know the average. So let's take a look and see how far each of these numbers is from 50. So in this first list, 1, 1, 1, 1, all 1 unit away from 50. I'm not going to put -1, like 49, I'll put maybe -1, 51, +1, because we know the average is 50. And so since we know the average is 50, we're just looking about how large is the spread. But furthermore, when we learn how to calculate the standard deviation, you'll see that, well, I mean, I can go ahead and tell you this right now because we'll use this in this video, but what the standard deviation is, and we'll go through the details of this calculation in the next video, but the standard deviation is you get the deviation of each of the values from the average and then calculate the root mean square of those deviations. And so root mean square, those numbers, remember, it doesn't matter if there's a plus or minus on the numbers because you're squaring them. You're squaring the numbers, summing those squares, taking the mean of that, dividing that by the number of data points, then taking the square root. All right, so with that in mind, we know that the standard deviation of this list of numbers is going to be 1. So obviously we're going to pick 1. From 1, 2, or 10, we're going to pick 1. But this might be a little confusing to you because, well, and if the standard deviation is 1, in this case, every single one of these data points is within 1 standard deviation from the average, right? Well, didn't we say that it's like the general rule was 68%? That's a general rule. That's for the majority of cases, especially when you consider randomized controlled experiments, observational studies that are as randomized as possible, that's what's going to be the case. So in other words, if for the Haynes study, the Haynes 2 study, the boys age 11, their heights, if you calculate the average and then for each of the boys' heights, find the distance of that height from the average. So now you have all these distances from the average, all these differences in heights from the average for all the boys. Calculate the root mean square that's going to be the standard deviation. And then if you compare each boy's heights to how many standard deviations they are away from the average, in general, for you're thinking about a randomized experiment, randomized data points, as randomized as possible, it's going to be that 68%, 95% rule. But here's a list of numbers that's not the case. So it's just a general rule that for the most part, for when you think about controlled experiments, randomized data collection, it's going to work out that way, that 68%, 95%. But the standard deviation is as far as calculating the spread, if you would look at this and you wanted to get a value for that represents the spread of this data, from the average of 50, you'd want it to be 1, right? That's exactly what this is, literally. Each one of these is one, each one of the data points is 1 unit from the average. So if you wanted a metric to represent the spread of this data from the average, wouldn't you want it to be 1? Yeah, and that's what it is. Okay, next. This is 2 from 50, 2, 2, 2, 2, 2, 2, 2, 2. We know the average is 2. So all of these are two units above or below the average, so this standard deviation we expect to be 2. Okay, again, each one of these, the average is 50. So here's this 2 units, 1, 1, 2, 3, 2, 4, 1, 3, 1. So looking at this, I would expect something, definitely not 10, but I wouldn't say 1 either. We've got just 3 1s and a bunch of 2s, and then a 3 and a 4 in there, or 2 3s and a 4. So I would say 2 on this one. All right, 4 1 4 1 1 3 0 0 1 1. I would say 2 on this one, not 1. Well, maybe 1 because we've got these zeros here, so that's going to pull it down. We got 2 zeros, 4 1s, or 5 1s, then 2 4s. I would say 2, but I wonder, let's see, what is the standard deviation here? So let's calculate the root mean square of these numbers here. We've got 16 plus 1 plus 16 plus 1 plus 1 plus 9 plus 1 plus 1 divided by, there's 10 numbers, and we're going to take the root of that. So 16 times 2 is 32. 32 plus 9 is 41. 42, 43, 44, 45, 46 divided by 10. So 2.1. Okay. So it's, yeah, I thought maybe it would be like 1.7 or something, 1.6, but no, it's 2.1. So definitely 2. Okay, what about this one? This is 10, 14, 19, 0, 2, 0, 4, 6, 12, 3. I mean, this is going to be 10. This is, of the 3 options, we would choose 10. It's not 1. You know, you got 0, 0, but you got 12, 3, 4. Yeah, I would say 10. If we calculated the root mean square of these numbers, it would be closer to 10 than it is to 2 or 1 for sure. Okay, the standard deviation for the ages of the people in the Haynes 5 sample is around what? Fill in the blank using one of the options below. 5, 25, or 50. For the ages of the people in the Haynes 5 sample. So if we go back to section 2, they don't give us any data on the average age. So I guess they just want us to think about it, use common sense, you could say. So I thought the ages were 18 and over, but I guess not. Okay, so you could think, well, the average age, maybe we say it's 85 divided by 2, but which would be what? That'd be 42.5. But you would think that it would be, the average would be less than 42 because there's probably more younger people in the population than there are older people, assuming that they didn't deliberately decide, okay, we're going to do this many old people, this many young people. I guess from what I remember, they were just randomly selecting out of the population of people. Okay, so if we assume the average is 35 years old, but I think even if we assume the average was 42 or 43, we'd still get, based on these options here, we could still get the answer. But if we assume the average age was 35 years old, the average age of each person in the study, right? If the standard deviation was 5 years, well, then people that are 85 would be 7 or more standard deviations away from the average. And I mean, it's not that that's not possible, but there would only be, in that case, there would be like one person that's 70 or older, or 2 at max. You know, it'd be very small. And there was no indication that there wasn't, you know, a decent number of senior citizens to do like statistical analysis on. When we went through that section, they had elderly people with their own average for the histogram. So if that's the case, then elderly people should be within 2 standard deviations. So no, not 5 years. Let's go to the other extreme, 50 years. Well, okay, if the average is 35, then 35 plus 50 is 85, and then 35 minus 50 is even below 0. So this doesn't seem to make much sense. Again, if we're assuming that it's like this kind of randomized list of ages, and so most likely it follows that 68%, 95% distribution, then in this case, if it's 50 years, the standard deviation is 50 years, then every single data point is within 1 standard deviation, which is not impossible. We saw that here, but, again, if we think about the experiment, it was this randomized experiment. You had this study, and yeah, what they're suggesting here is that it's not like they said, okay, we're going to interview this many number of old people, this number of this age range, this number of this age range. It was more, they just randomly selected from the population. So if that's the case, then we wouldn't expect to have some pattern like this, definitive pattern. We would expect more of that, kind of more randomized, that 68%, 95% standard deviation type distribution. So in which case, all of these would be within 1 standard deviation. And even more than that, this, when you go below the average, this goes off the map. It goes off the scale. So no, it's got to be 25 years. So 25 years, 35 plus 25 is 60. 35 minus 25 is 10. Yeah, there you go. That's 1 standard deviation away. But that still leaves some of the age groups that could be 2 standard deviations away. But you could see, even if we chose the average to be 42 years old or 45 years old, the same logic would have worked. Below are sketches of histograms for 3 lists. Match the sketch with the description. Some descriptions will be left over. Give your reasoning in each case. Okay, so some descriptions will be left over. I'm not sure what they're saying there, but all right. First thing to notice is that the areas of each one of these histograms are symmetrical. The areas are. So these two, the entire histogram is symmetrical, but the entire histogram is not necessarily symmetrical. I guess if you ignore the axes, then it is, but you can think about this. We talked about how you can think about this like if this was test scores going from 0 to 100. Well, you don't want to erase this part of the axes because it's descriptive. You want to see the full range of possible test scores. So in that case, if you look at it that way, this entire histogram is not symmetrical, but the area still is. And so when you're just thinking about if the area is symmetrical, that means that the median and the average are going to line up at the same point. So the median and the average for each one of these histograms is going to be at the symmetry point of the area. So, and again, we're thinking the median and the average. Remember, histograms behind the scenes is a list of numbers. You can calculate the median of a list of numbers. You can calculate the average of a list of numbers. You can calculate the standard deviation of a list of numbers. Okay, so now let's match these up. So the average here is 3.5, 3.5, and then 2.5. Number 4 here is not going to be associated with any of these graphs. The average is 4.5. Okay, average 3.5, now average 2.5. So one of these two, or I guess maybe both, is going to match to this graph. Definitely not to either of these two graphs. So which one? Standard deviation 1 or 0.5. So the entire data set is within 2.5, 3.5, is within 3.5 or one unit. You go from 2.5 to 3.5, 2.5 to 1.5. So the entire data set is within 1 unit from the origin. If we're assuming the general behavior of a list of numbers, then everything being within 1 standard deviation is not typical. Again, this was the case where for these two lists, everything was within 1 standard deviation, but in general, that's not how you're thinking about it. If it's like more of like a kind of randomized list of numbers, like experimental data is typically what that is what you're thinking about. So the standard deviation 1/2 makes more sense. In that case, all this data is within 2 standard deviations. So this would be number 5, and then we could cross this out. I mean, we can try. Let's draw the histogram for this. So, all right, we've got 50. Okay, so we know that this is symmetrical because the median and or is it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? You'd have 5 49s and 5 51s. So yeah, the median is 50. But then you would have 2 blocks of the same height on 51, like that. That's the histogram for this, for list A. It would be the same idea with list B. Okay, so again, this histogram, the entire histogram is within 1 standard deviation from the average. Okay, but again, a more typical histogram is going to show a distribution around the average that goes by that 68%, 95%, 68% within 1 standard deviation, 95% within 2. So this is not a typical distribution that you see from like a more of randomized list of numbers. If we look here, this is more in line with what we're going to see in chapter 5. It's a curve kind of like this, right? So about 68% of the total area is within 1 standard deviation, and about 95% of the total area is within 2. Here, if you go 1 standard deviation away, all of the area is within 1 standard deviation. And so what's the difference, though? What's the difference between a data set like this and a data set like this? Well, this is more of a unique case, these two. The entire data set is just 2 values. That's not usually if you do like a survey or a random selection or something, you usually just don't have 2 values, right? So you see here, there's different values. There's a bunch of different values, not just 2. And same here, there's different values. I'm not sure if this allows for like 1.5 and 2.5. You know, this doesn't allow for like 49.1 or anything, but still there's different values here. Okay, so anyway, these two have an average of 3.5. What's the spread here? This is spread out, so 3.5, 4.5. This is spread out 1 unit on each side of the average. So we would expect the standard deviation to be less than 1. So we'd say this is number 2. All right, here the data is spread out, 3.5, 4.5, 5.5, 2.5 units on each side. So standard deviation of 2. Well, no, probably standard deviation of 1 would make more sense. This looks to be about 68% of the total area. And then 2 standard deviations, that's about 95%. So we'd say this is number 1. All right. Hypothetical. In a clinical trial, data collection usually starts at baseline. When the subjects are recruited into the trial, but before they are randomized to treatment or control. All right, so you select the subjects, but they haven't been randomized yet, but data collection could still start, and they call that baseline. Data collection continues until the end of follow-up, okay? So even after they've been randomized and they've gone through the main data collection experiment, whatever it is, even after follow-up, data collection continues. 2 clinical trials on prevention of heart attacks report baseline data on weight shown below. In one of these trials, the randomization did not work. Which one and why? Okay, so I guess, yeah, you could tie weight to heart attacks potentially. So the treatment and the control would be, the treatment would maybe took some sort of heart medication, control didn't. And so here, the treatment group, they've got a sufficient number of persons on each group. The treatment group, the average weight was this. The control group, the average weight was this. So the control group weighs less. That could be a confounding variable if you're doing this for like heart medication. But in this trial, the treatment group and the control group had the same average weight. So you would say that the randomization didn't work here because you have a big confounding variable in there between the treatment and control. But we're talking about the standard deviation in this section, so let's take a look at the standard deviation. Here, the standard deviations are the same. Here, the standard deviations are the same between treatment and control. And then between these 2 trials, the standard deviations are about the same. So what could we look at? What can we potentially, information can we gain about these standard deviations? I guess the way you could look at it is potentially if the treatment group and the control group, they had different average weights, but they had different standard deviations. Maybe you could say that because of the difference in standard deviations, you could ignore this potential confounding variable. But what this tells you is that if you have the same average and the same standard deviation, for the most part, that would suggest similar histogram curves. And so if you have one curve that has a certain average and a standard deviation, and you have another curve that has a different average but the same standard deviation, then it's almost just like shifting that curve, a pure shift. You go from here to here. So that just makes this clearly more of a confounding variable, right? If this standard deviation was a good bit different, then maybe you could draw the two curves and say, well, there's enough crossover and it's not a confounding variable. But here it's just a shifted distribution curve, and that's not what you want if you want to have a randomized similar treatment and control group. Okay, one investigator takes a sample of 100 men age 18 to 24 in a certain town. Another takes a sample of 1,000 such men. Which investigator will get a bigger average for the heights of the men in his sample? Or should the averages be about the same? Okay, well, the averages should be about the same. So you're assuming in this town it's just a random sample of men, age 18 to 24. They're being selected randomly for whatever this is. So assuming both are selecting to some degree a sufficient number of men, then the averages for the heights, the average of the heights should be about the same. Yeah, if this guy was just selecting 10 men, the first guy, and the second guy 1,000, well, then maybe he just gets lucky and selects two really tall men, and then some other ones that are more of above average height, and he gets a different average. But if he's selecting 100 from the same population, if both are selecting what you would say is a sufficient amount, and I can't give an example right now of what a sufficient amount would be, but 100 seems sufficient, and so these are both sufficient amounts, the averages should be the same. It's the same population. Which investigator would get a bigger standard deviation for the heights of the men in his sample? Or should the standard deviations be about the same? Okay, so the standard of these 100 men, the heights, there's going to be a certain standard deviation. Same thing with this 1,000 men. The standard deviations should be about the same, just like the average. Okay, which investigator is likely to get the tallest of the sample men? Or are the chances about the same for both investigators? And then D here is saying the same question, but for the shortest. So yeah, this is interesting. What you can think about here is, okay, we have a list of numbers. You have a list of 100 numbers here, a list of 1,000 numbers here. You can arrange those from shortest to tallest, and then you can calculate the average, the standard deviation. You can also calculate the range, the tallest man's height minus the shortest man's height. Well, okay, we expect the average and the standard deviation between these two to be about the same, but the range, we would expect the larger sample to have a larger range, which is the same thing as saying that which investigator is likely to get the tallest of the sample, like to find the tallest man and the shortest man. If you find the tallest man, you're going to have a larger range. If you find the shortest man, you're going to have a larger range. And the reason is because, okay, the average and the standard deviation is more of like an inherent statistical characteristic of that population. So as long as you're taking a sufficient sample size, you should find those values for the average and the standard deviation. The range is more related to who gets the tallest man in their sample or the shortest man in their sample. And so what that's kind of like is if there was one 7-foot tall man in the entire population, well, then which one of these investigators is likely to find that tallest man? Well, the one that's selecting 1,000 men. You see the difference? Well, you might say, well, how doesn't that affect the average? Well, first of all, it doesn't mean that it says most likely. It doesn't mean that if you did this, that the guy that selected 100 men would have the tallest man of both of these. That could happen, but you think about the likelihood. So that's the first thing. But the second thing is, if this town has 10,000 people, there's probably only one man that's over 7 feet tall. So as far as the overall average of the entire population, he's not going to affect it that much. He's just one person. So even if finding the average, this investigator happened to select the tallest man, the 7-foot tall man, you would think, okay, 100 data points is still sufficient to smooth out the effect of that tall man to get the correct average and standard deviation, but it probably would affect it. It would probably mess it up if he happened to select the 7-foot tall man. It would make the average a little off than what it's supposed to be, as compared to if this investigator found the 7-foot tall man, the rest of the other 999 people should smooth out the effect of that tall man to get the expected average. So both of both investigators have a similar average and standard deviation. But because of random chance of just selecting someone that's very tall or very short. You would expect the range of the person selecting 1,000 men to be larger than the range of the 100 men list. Okay, the men in the Haynes 5 sample had an average height of 69 inches, and the standard deviation was 3 inches. Tomorrow, one of these men will be chosen at random. You have to guess his height. What should you guess? You have about 1 in 3 chance to be off by more than blank. And here are the options. Okay, so let's make sure we understand what they're asking. The men in the Haynes 5 sample, which was the 0304 sample, had an average height of 69 inches, and the standard deviation was 3 inches. Okay, so of the full list of men, if you take all their heights from the Haynes 5, of all of the men, any age, the average was 69 inches, and the standard deviation was 3. Okay. Tomorrow, one of these men will be chosen at random. So one of the men from the study, not like the men from the general population, one of the men from the United States at that time. No, one of the men from that list, okay, will be chosen at random. You have to guess his height. What should you guess? Okay, this is a little confusing. The answer here is that you would guess the average, okay? But let's come back here. If we were going to select try and predict, okay, we're going to select a number from this list, try and guess which one it is. We wouldn't we wouldn't say the average. We wouldn't say 50. There's no chance of none of these are equal to 50, but the average is 50. So how do you interpret this? Well, the general idea is that you might say, well, do we select? So if you come here, if we're trying to select, I guess it's the same thing. This histogram was for women, 2,696 women. What do you want to guess? Which value do you want to guess? That if you're going to select from this 2,696 women, one woman, and you want to guess what her height's going to be, you select whichever height has the most number of data points. That's what you're going to guess. So what does that mean? Is that the spot that has the tallest peak? Yes, from the standpoint of that, if you're selecting one height value, then you can imagine, making tick marks between all of the possible height values. And then since all the widths of all those tick marks are the same, you're just looking for which one of those tick marks, or which in between those tick marks, which has the highest peak, which is the tallest. That's going to have the most data points at that height value. That's just a measure of we call that the density. But if you had like a really tall, skinny peak at one point, and then a shorter peak, but that's wider, and you're talking about, okay, I want to guess if, I don't know how to describe it, but like if a number's going to be within this certain range, then it's really more about you want to guess a value that has the larger area. It's really more about area. Like the number of data points is proportional to the area, right? Not the peak. It's the area. But if you're just talking about one height, you're trying to guess one height, well, then you can break up the horizontal axis into between all the height values, so the horizontal widths of the each piece are the same. So now you're just looking at the heights. You see the difference? And so just looking at this, though, the back of the book says the answer to this question is you would select the average. But here, to me, if you're gonna try and take, you're gonna select one woman from this 2,696, this population here, from whatever made this distribution, you're going to select from that group and then try and guess the height. Well, I would select one of the numbers that's under here. Not this the same width, not one of the numbers that's under here. It's the same width, these two blocks. There's more data points here. This vertical line is where the average is. Why is the average here? Because we talked about the average needs to balance the data points. So you have more numbers further out, so the average is moved out. So in this case, the back of the book says average. I would say that you would find the peak point. And I say the peak point, again, because they're not asking us, it's not that you don't look for the peak point to get the highest probability of, like, if you're going to select something from that population, you select where the largest area is. That's where the most data points are going to be. But if you're selecting one value, and like you're not saying, okay, if I want to try and select something, should I select from within this range of values and this other range of values? Well, then you got to compare it. Does one of those ranges is larger than the other range, which would make, even though there's a taller peak in one range, the total area of the shorter peak is larger, well, then you want to select from that one. But if you're just talking about one height value, you go wherever the peak is. And I just looked back, they don't give us a histogram from the Haynes 5 study for the average height of men. So, well, okay, let's just say we guess the average. I think they might be saying the average because if, that 68%, 35% rule, or no, it was 68%, 95% rule for the you can think about the general way that a list of numbers is distributed. In that case, the average is the peak point. It's like we're going to see in chapter 5. It's like a normal distribution, they call it. The center point is the average, and that is also the peak point. So you would guess the average. That's probably what they're going for, because they say here, in that case, if you're thinking about the general rule, then you have about a 1 in 3 chance of being off by more than what? It was 68%. Yeah, that's probably what they're talking about. If you assume the general distribution, then you would guess the average. Yes. If you know the distribution, if you know the histogram, then go to the histogram and see where's the actual peak point at, or where's the actual largest area of what the question is asking me. Wait, no, it wouldn't be 68%. So 68% of the data points are within one standard deviation. One standard deviation is 3 inches. So 3 inches. Because we're selecting from the same population that the study was done on. Those list of numbers that they use to calculate the average of 69 inches and 3 inches, we're selecting a man from that list. So we're not saying we've got this list of men, now we're going to go select a man from the general population. What would you guess the height to be? We haven't talked about that idea yet. They're saying from that literal list of men, if you want to guess his height, you would guess a height of the average, and you would have a 1 in 3 chance, that 68% chance of being off by a standard deviation, 3 inches. All right. As in exercise 9, but tomorrow a whole series of men will be chosen at random. After each man appears, his actual height will be compared with your guess to see how far off you were. The RMS size of the amounts off should be what? Look at the bottom of the page. Yeah, that's what we talked about. The standard deviation is the RMS deviation from the average. Tomorrow a whole series of men will be chosen at random, chosen from the literal list. I want to make that clear. They're not saying that you sampled you did a sample of men from a population, like a town, and then that sample, there was an average height of 69 inches, standard deviation of 3. Now you're going to go choose a man from the population, from the town, and you're trying to guess his height. No, that's not what we're doing here. We're going to talk about that idea in a later chapter. They're saying in this Haynes 5 study, they sampled, 1,000 men, 3,000 men. They had a list of the heights. The average of those lists was 69 inches, and the standard deviation was 3 inches. And now we're going to choose a man from that same list. You see the difference? And so if now we're choosing a whole series of men at random from that list, and his actual height is measured and compared with your guess to see how far off you were. Those amounts off, you get the RMS of it. That should be the standard deviation. If you kept going and you eventually chose the series of men you selected was the total amount, 3,000 men, the RMS of the size amounts is literally going to be the exact same standard deviation here, literally. But we talked about at the beginning of this video, if you know of a population, so like let's call the 3,000 men in this test a population, and you take a sample from that, then if that sample is large enough, you should get the same average and standard deviation as that the population. So we would say this RMS of the size amounts off should be 3 inches, the standard deviation.